Here we introduce our work on 4D reconstruction and streaming based on 3D Gaussian splatting, which is titled Dynamics-Aware Gaussian Splatting Streaming Towards Fast On-the-Fly Training for 4D Reconstruction. The development of 3D Gaussian splatting has inspired works in the area of 4D dynamic spatial reconstruction, or free viewpoint video construction. However, current popular methods typically take the full-length multi-view videos as input and perform 4D reconstruction. This line of work relies on non-causal full-length videos, therefore fails to deal with on-the-fly training and per-frame streaming, and cannot support applications like live streaming and online gaming. Aware of this vacancy, we are motivated to investigate how to use per-frame causal input for 4D reconstruction. In this pipeline, we iteratively reconstruct the space at each frame, from the previous frame representation and the current frame multi-view inputs, and perform on-the-fly training to yield the pre-frame representation. In this vein, we need to model the differences between frames in 3D space, which is much more complex than modeling the flow in 2D videos. To support a fast on-the-fly training, we need to consider both the reconstruction quality and the training speed. And the aim of this work is to effectively model the differences between frames in 3D space and achieve high reconstruction quality while reducing the training time overhead. Towards this, we design a three-stage pipeline for iterative streamable 4D reconstruction. Here is the overview of our proposed pipeline. This three-stage pipeline applies for each frame iteratively. The optimized representation consistently serves as an initialization for the next frame. Our method effectively utilizes the intra-frame dynamics properties and inter-frame temporal relationships. Specifically, the selective inheritance stage adaptively selects the densified Gaussian from the previous frame. The dynamics-aware shift stage separates the Gaussians into dynamic Gaussians and static Gaussians, and apply different levels of deformation fields to learn their shifts and rotations. The error-guided densification stage recovers the newly emerging objects that do not exist in the previous frame. Here we give a brief introduction of each stage in our proposed method. In the selective inheritance stage, we selectively preserve the densified Gaussian primitives from the previous frame to exploit the temporal continuous information. We assign a learnable parameter to each Gaussian primitive, normalize it into the range of 0 to 1 and then quantize it to a binarized value. This binarized vector decides whether to keep this Gaussian in this frame. This learnable parameter m is optimized towards a loss combined with fidelity loss and mask loss. This loss encourages the optimization to preserve the Gaussians, which are beneficial for the rendering, and remove the Gaussians, which are redundant for the current frame. Then these inherited Gaussians and the base Gaussians flow into the next stage. The dynamics-aware shift stage deals with the deformations of the previous frame's Gaussians. It is noted that, in a natural scene, most of the objects including the background present only minimal changes or remain unchanged, while the dynamic parts such as humans and animals experience highly dynamic motions. Therefore, we propose to separate the dynamic and static Gaussians in the scene. We initialize the frame with Gaussian grouping, providing scene segmentation results, and infer the optical flow between consecutive frames. Based on the magnitude of optical flow, we detect the dynamic regions, and align these regions with the segmentation results to find out the dynamic object IDs, and then progressively the dynamic Gaussians. For the dynamic Gaussians, we assign a dense hash encoding-based MLP, to optimize their complex motions and variations, while for the static Gaussians, a simpler layer is assigned with a quarter hash table size and halved feature dimension, to rapidly learn the simple deformations. This Gaussian shift process transforms the Gaussians from the previous frame to fit the current frame. For the weak reconstruction areas, and the recovery of emerging objects that do not appear in the previous frame, we rely on the densification stage providing an adaptive solution. Previous 3D Gaussian splatting-based methods densify Gaussians with large positional gradient. In our method, we propose to include the errors from the previous stage into consideration as well, to enhance the detection of weak reconstruction areas. Specifically, we collect the error maps from the previous shift optimization stage, determine the high distortion areas in 2D plane. Then we project the 3D Gaussian positions onto 2D plane and find out the Gaussians falling into these high distortion areas. Based on this, we design an adaptive densification. For the general area we use the positional gradient indicator, and for the high distortion area we assign a lower threshold for densification, therefore it fast densifies and recovers the emerging objects in high distortion areas, progressively supports a fast on-the-fly training. With these three stages, our proposed pipeline exploits the temporal continuity facilitating efficient training, accommodates deformation of existing Gaussians through a dynamics-aware design, effectively densifies, and recovers weak reconstruction and emerging objects. Here are the experimental results and comparisons. Higher PSNR indicates higher reconstruction fidelity, less training time indicates fast on-the-fly training speed. The size of the marker represents the frames per seconds, indicating rendering speed. Considering these metrics, our method achieves a state-of-the-art on-the-fly training performance, obtaining per-frame training within 10 seconds. On the quantitative results, our method achieves highest reconstruction quality among online training methods, and even surpasses most of the offline methods. Here are some visualizations, showing that our method achieves vivid reconstruction and higher fidelity details. We also visualize the dynamic Gaussians detected by our proposed pipeline, which effectively and accurately guides our method to recover the complex motions and details. It is also recommended to refer to more methodology clarification, implementation, additional experimental results in our main paper and supplementary materials. Thanks for watching.